guys, I'm Brian.
And I'm Alyssa, and welcome back to another Demo of the Week. Today, we're going to be talking about the Meissner effect with superconductors.
First, we have to talk about how magnets work. Magnets are objects that produces their own magnetic field, which makes magnetic force, which we call flux.
The force of the field comes out of the north end of the magnet and flows into the south part of the magnet.
So what if you put two magnets together?
Well, I think we've all seen that before. The opposite sides attract, and so they come closer together, but like charges will repel and go away from each other.
But what about things that magnets attach themselves to, like iron or nickel?
Well, they have unpaired electrons. Those electrons have the same spin as the magnetic force, so the electrons and the magnetic field will attract each other.
However, when you put a magnet next to an object without a magnetic field, the field just passes through it.
But wait, Brian. There are these really super special non-magnetic materials in this world called superconductors.
So when a superconductor is at room temperature, they do not interact with the magnetic field, but when they cool below the temperature, they will reject all the magnetic field that's around it.
That's right. And this interesting concept is called the Meissner effect. Now, there are two types of superconductors. The first type of superconductors are normally pure elements, like lead, mercury, aluminum. There's a second type of superconductor. These superconductors are compounds instead of pure elements. That means there's impurities in them.
Wait, since there are impurities, does that mean only some of the material becomes a superconductor at the critical temperature?
Yep, that's right. The material partially expels the magnetic field, but we'll let some of the magnetic field go through as well.
Okay, so the magnetic field slips into the gaps of impurities and pins the material in place in a process called flux pinning.
Yeah, and this means that the superconductor will levitate. Let's go try it.
Okay. Right here we have a ceramic type 2 superconductor called yttrium barium copper oxide, YBCO for short.
For a singular element to become a superconductor, it will need to get to extremely low temperatures, close to the single digits of Kelvin. But for YBCO, it has a critical temperature of 93 Kelvin, which translates to about 180 degrees Celsius.
Okay, so even liquid nitrogen is colder than that, with a boiling point of around negative 196 degrees Celsius.
So, we're going to use some liquid nitrogen to cool down the YBCO to its desired temperature.
Okay.
The YBCO has been chilling in the liquid nitrogen for a few moments now, and it has cooled to its critical temperature, allowing it to act as a superconductor.
Now we're going to put the magnet on top and see what happens.
Whoa, the magnet's floating.
Yep, the YBCO is repelling the magnetic flux caused by the magnet.
Normally, the magnet would slide right off, but since YBCO has impurities, these impurities are causing flux pinning, keeping the magnet in place.
Alright, scientists, that's all we have for this week.
We'll see you guys next time for another
Demo of the week.